Okay, I'm going to continue the video I left off yesterday, talking about kinetics, and I'll go through what you're going to do on lab next week. So please email me questions or come see me in my office. I'll be in my office on Monday. I've got virtual hours today. So let's get going with this. Let's set it up. Okay, today we're going to continue with the kinetics discussion, and kind of I'm going to overlap some of the features associated with this. Okay, what I'll do is go back to this slide first. Okay, now I'll share the screen with you. Okay, now to determine the rate constant for the following reaction, and I want you to look carefully at this. The key thing to understand about the nature of rate constants and how they work is essentially if you vary the concentration, when you vary the concentration, the rate changes. So essentially varying the concentration, the rate will go up or down, okay, depending on what you're dealing with, okay? And in this case, the way to determine the rate law, and again, the rate has to do with if you have A plus B goes to AB, the rate essentially has to do with the rate is equal to the change in A, the negative change in A concentration divided by the change in T or the time. And it's negative because this is decreasing. Whereas the AB is also equal to so essentially plus delta AB as it goes up. So essentially this is the nature of how these essentially work. So again, it's very important to understand the distinction, but then the other way you have it is related to the concentration of A and B. So essentially the rate will be equal to the rate constant for this times the concentration of A and the concentration of B to the X and the Y power, depending on what kind of reaction you're dealing with here. And essentially, we'll get into that later. But again, the key thing to understand about the nature of the rate laws regarding the way they work, it determines essentially with this problem, you have these things. The rate is the decrease of methane in relation to time. Okay, and then you've got minus 1/2 the oxygen change over time. And then you have the concentration of CO2 going up there, as well as the concentration of water going up, and you include 1/2 of that in there as well. Okay, so the rate law expresses the relationship of the rate of reaction to the rate constant, and the concentrations of reactants raised to some powers. So essentially, if you have a problem like this, the rate will equal this related to each of them. And essentially what we have here now is a combination of factors where you've got the rate constant there, then the concentration of A, which is here, and then the concentration of B, and they have a relationship between each of them. So the reaction is X order in A. So for example, it could be 1, 2, 3, it could even be 1/2 in some cases. And Y can also be the same thing, 1, 2, 3, etc. Okay. And it's Wythe order in B. Now the overall reaction is X plus Y when you have that relationship. Okay, so now let's look at an example here. When you look at the different values, the rate here is equal to the rate constant times the concentration of fluorine to X power, and the concentration of chlorine to this one, to the Y power. And basically the way you determine it is experimentally. This is times 2. And if you notice the difference between these, this also goes up by 2. And then you compare the other two here with this one and this one, and then you see what the relationship there between those are, and that's determined experimentally. And that's what you're going to be doing next week. If you double the concentration of fluorine, the concentration of chlorine dioxide will change also, okay? If you quadruple CO2 with the fluorine constant, essentially it goes up, the rate will quadruple also, so they both are equal to 1 for each of them. Now, a summary of the rate laws. Rate laws are always determined experimentally, and that's what you're going to be doing next week, is determining the rate law for the particular reaction we're going to work with. And I'm going to talk about that reaction after this little lecture. That will be the pre-lab lecture. Reaction order is always defined in terms of the reactant, not the product concentrations. So the key thing to understand about the nature of the reactants is they have to collide. They have to collide together to react and then form a certain form. Has someone joined me? Okay, well, in any case, the reaction essentially order is always defined in terms of the reactant, not the product concentrations. So essentially the key thing to understand about that is you've got a combination of factors related to each of them, and hopefully you can see how this all works together. Okay, so I'm going to stop the share for a second and stop my video here. Back to the share the screen. The reaction order is always defined in terms of the reactant, not the product's concentrations. Okay, so basically we got a combination of factors related to the rate as well as the reaction order. The order of a reactant is not related to the stoichiometric coefficient in the reactant in the balanced chemical equation. So the order, if you go back to the previous one, the order of this reaction is not related. Notice this, there is no 2 there. This order is not related to the Y. Not related. Okay? And the X is not related to the F. It's all dependent on a variety of factors, collisions, proper orientation, etc. And here's an example here. You've got fluorine reacting with chlorine dioxide to form that product. The rate is equal to there, with those each being 1. And you notice the rates do not determine. Now let's look at the next one here. Determine the rate law and calculate the rate constant for the following reactions of the following data. Well, you look at these different values. Notice this one stays the same, and this essentially shifts downwards. Okay, with this concentration staying the same. This one doubles times 2. This stays the same, and then essentially this goes up like that. But if you double this related to that, this goes down by half. So essentially there's a relationship between each of them. So the rate there is equal to that you double the rate associated with that. You have the I, the rate doubles according to that, essentially double the I there. The rate doubles, experiment number 1 and number 2. See, doubling the I going back this way, double the I going back that way. And if you double the concentration of the S2O8 between that, experiment 2 and 3, that also doubles. So the rate constants for each are equal to 1, and the total is going to be equal to this. And then you plug this back in here because, again, the rate is equal to K times the concentration of A and B. So you just rearrange this, bring this down there, and then you get that equation, and you can plug the values in and see what the rate constant is. And you're going to figure out what the rate constant is next week. Now, there's certain kinds of reactions associated with this. When X or Y equals 1, it is called first order, if that's the only one that's involved, okay? And basically, A goes to a product, you have that. The rate is equal to A, the concentration of A, and essentially that is essentially directed to this. An example of this would be like, say, for example, you have potassium carbonate, and then you go to form sodium oxide plus CO2. So that rate constant would be dependent on this one there. It's sodium carbonate. So that would be a factor of 1 in this conditions, but we don't know precisely because that has to be determined experimentally, but it's important to keep those in mind regarding how those all work. The K is the rate over the concentration of A, and that essentially is moles per second divided by moles, so it ends up being reciprocal seconds for the rate. That's the unit for the rate constant. A is the concentration of A at any time t. A0 is the concentration of A at any time t equals 0. And then, for example, if you graph this, you get a relationship here between A and A0, and this is where a little bit of calculus comes in, but this general chemistry does not include calculus, so we just use the formulas to help us understand that. And then if you were to take the log of both sides, you get this relationship. The log of A equals the log of A0 minus KT, because this minus KT here goes into that form. And that's the nature of a first order reaction as to what it looks like. Now, the graphical determination of K, this again is an experiment that you would do that to determine this. The slope in this case is the change in Y over X. And you plug the values in to see the different values of Y and the values of X there. And so the slope is going to be equal to the rate constant in that case. And in this case, it's K equals 5.7 times 10 to the minus 4. The reaction 2A goes to be its first order in A with a rate constant of 2.8 10 to the minus 2 minus seconds. How long would it take for A to decrease from 0.88 to 0.14 molar? Well, you got to set up the equation first. The rate will equal minus 1/2 because of this 2 times the concentration of A divided by the change in temperature, change in time. Okay, and you go by the rate order. You said it's first order, you use this other equation here related to that. You have A0 is 0.88 molar, A is 0.14. So the KT is equal to that value. The T is equal to the time is equal to the difference. So you plug the values into the equation, and then you can figure that out. This is one reason you got to use your scientific calculator to do these kind of questions. So we see that the time is 66 seconds. But again, these numbers are put in here to determine that. The half-life is the time required for the concentration of reactant to decrease to half its initial concentration. So if you have 8 grams, it'll go down to 4. So when you have A equals A0 over 2, you can plug those values into it like this. T the half-life log A0 over A0 divided by 2 divided by K. And then you get the relationship there, and that's the half-life for a first order reaction. What is the half-life of N2O5 if it decomposes at a rate constant of 5.7 times 10 to the minus 4? Well, again, you plug it in the equations. Okay, you plug the values into it, then you get 1200 seconds or 20 minutes. How do you know a decomposition is first order? Well, basically, it's by checking to see what the half-life would be. If it follows that equation, that's the half-life. Okay, first order reaction, A goes to a product. That's the first order reaction. The number of half-lives there, you have one half-life. There you have essentially one half-life after one half-life, A0 over N. You have 2, it becomes 4, 3, it becomes 8, 4, it becomes 16. Second order reaction is when you have 2 of them associated with this. And this is where you would have a rate be equal to, for example, you have a rate here where you can have the K times A times B, because that's 1 plus 1. That's also second order. Or it can be this one here with 2. Or you can have whatever combination you have for each of them. Like it could be 0 or 2, etc., related to a whole variety of different kinds of reactions. If you plug the values in there regarding the K, there, the reciprocal is 1. The rate is going to be in there, M, molality, 1 divided by molality seconds, and you plug the values in there. You then do the logs associated with each of them. A is the concentration of A at any time T. A0 is the concentration of A at time equals 0. You plug the values in there for each, and the half-life is going to be equal to that when you have a second order reaction with A alone. Zero order reactions are when essentially the concentration of the reactant doesn't matter. So a zero order is where you have the rate is equal to the K times the concentration of A to the 0 power there. And essentially that would be equal to 1. This makes that equal to 1. For a zero order reaction, A goes to a product. And you notice that the rate is just equal to the K constant associated with that. And the units in that case would be moles per second. And if you look at that relationship between both of them, A is the concentration of A at any time, T, and you plug the values in, you rearrange it, the T 1/2 is equal to T when A equals A0 divided by 2. You plug the values in there associated with that, and that's what the curve will look like. Summary of the kinetics, the first order, second order, and zero orders, first order and second order reactions. You have an order rate law, the rate equals K. The concentration time equation there, the half-life is that. And the problems that you have in the book, as well as in the lab, would be related to using these equations. So these equations will be provided for you. And that's just important to keep in mind, okay? Now, when you have a reaction here, in this case, this is about what is called reaction mechanisms. This is essentially the nature of how that reaction occurs. This is the next topic. So with an exothermic reaction, essentially you have A plus B. And let me give you an example. If you have hydrogen reacting with chlorine to form 2HCl, you line up the hydrogen like this and the chlorine like this, like that next to each other. This forms a little bond, this forms another one. That's the activated state. This is called the activated state. And then the reaction could go this direction or back that direction again. So basically with an exothermic reaction, essentially it will go this direction primarily because this gives off heat. This is the delta H that you're dealing with, and essentially giving off heat will enable the reaction to continue that way. So most of the reaction will go that direction, but it can also go back the other way. And that illustrates the whole concept of what is called equilibrium. And we will talk about that in a later chapter, okay? So when they can go back and forth, but all reactions, even exothermic ones like this, will have an equilibrium aspect associated with it. But by and far, with this, you have an activated state, almost all will go in this direction all the way to HCl, just in its reaction together. But the activated state is like those two hitting in just the right orientation, and these bonds break, these bonds form, and then you end up going down there, and now you have 2HCl at the bottom. With an endothermic reaction, you have the activated state also like this. This is the activated state with an endothermic reaction, and then it goes off to form the product. Essentially, it's absorbed, and the activation energy is the minimum amount of energy required to initiate it. So essentially, this needs a push up the hill. Up the hill. That's called the activation energy. That is the activation energy. And for example, if you have paper and air, it doesn't catch on fire at normal room temperature. But if you strike a match to it, it'll easily burn. The match provides that activation energy for that reaction to take place. There's a temperature dependence on the rate constant. And the reason there's a temperature dependence is the higher the temperature, more collisions. And essentially, more collisions will cause more reactions. Very, very important. You've got to have those two reactants come next to each other to enable that to occur. The higher temperature will cause more collisions. You're essentially causing the atoms or molecule to move faster. And so they will hit the other material and then form the intermediate. That's the nature of all these reactions. Essentially, you have those two mixed together, and they'll move faster, and they'll form the intermediate. And again, the intermediate is, if you got this graph, it looks like this. The intermediate stage, this is the activation energy. This is the intermediate stage right here, and it's AD with a little asterisk up on top of there. That's the intermediate state. So essentially, you provide that extra things, and you add you increase the temperature, the reaction will occur much better, much faster. And this is the relationship, including temperature there. And again, this is called the Arrhenius thing, and this is determined experimentally. This is what chemists do. They get the relationship there. Now, because we have Presbyterian College and this is a Christian college, the way I love to look at it is that God designed it this way, and God designed science so that we could discover these neat equations and just the order that's in the universe, even that's in this Arrhenius equation that Dr. Arrhenius developed decades ago, basically is important to us understanding the world around us that God created. And that's part of the beauty of the nature of what we are looking at now, these relationships. Now, EA is the activation energy in joules per mole. R is the gas constant. And this is when you got reactions of gases. Okay. And again, gases are the easiest ones to move around at higher temperature. T is the absolute temperature there, and A is the frequency factor, and that again is also determined experimentally. The alternate format looks like this. Log K equals EA over R, 1 over T plus log A. But again, this is what's the most useful equation for the Arrhenius thing. And again, the type of problems you're going to have are going to be related to calculating what the constant is, or other things related to this here. The alternate form here at 2 temperatures, T1 and T2, you plug the values in there like this. You can look at the different relationship between both. And you got the log of K1 over K2 equals EA over R times the difference of the reciprocals of both. And you can plug it in that direction. That's the alternate form. And sometimes it's useful to use the alternate form. Now, molecular orientation. The orientation has to do with, for example, if you got a hydrogen ion, like a hydrogen molecule coming to the chlorine, and it attacks from that end, the intermediate would look like this. Okay, this is unstable, of course, and this will fall apart. But if you got the hydrogen like this, plus the chlorine like this, and it collides in just the right way, so you got these bonds forming and these bonds breaking, the result will be HCl here, broken off from HCl over there, and that kind of indicates the nature of molecular orientation when you're dealing with this kind of material. Okay, so let's look at this example here. This carbon monoxide coming next to the nitrogen dioxide, and it has to hit right at this place to grab that oxygen off. And then now you have the product there. So essentially, this bond formed at the same time the other one thinks. So if we have this like this here with a plus, that one and minus over here, and this comes next to it. So this has NO2 like this. So you have oxygen here with another oxygen down here. This will be negative. This will come and start forming a bond there between that. The result will be now carbon dioxide with double bonds on either side, plus an O on the other part, and we can have the oxygen now over here along with the N like that. And then there'll be a free radical associated with that. But that's essentially what they will look like. But the key thing is this bond forms while this one breaks. This is breaking here. And so then you'll essentially get that kind of rate. Or it could be the double bond down here. Yeah, it'll be that one, the double bond down here, here with the two there. And then this one will form. And then you got carbon dioxide plus the NO on the other side, like that. And again, it's all about how those things collide when you're going through the process. This is called an effective collision. If it has any other orientation, it's called ineffective. If it goes in that regard, they'll just bounce off each other. And this is ineffective. Now, what's going to happen if you increase the temperature? If you increase the temperature here with this, what do you think is going to happen? Yes, you'll get more effective collisions. Higher temperature, more of these. More, just because they're just more in frequency. More collisions, more effective ones. The overall progress of a chemical reaction can be represented at the molecular level by a series of elementary steps or elementary reactions. This is called the reaction mechanism. And basically it has to do with essentially acid and material forming intermediate first, and then you get the product at the end. And sometimes if they're making a chemical industrially, they got to add different ingredients. Now let me use an example here of, for example, calcium phosphate is a very important, calcium phosphate rock looks like this, okay? And essentially they react that to form diammonium phosphate, which looks like this. Okay, so essentially you go from this point to that point to dough. And this goes through a series of steps to enable that to occur. Well, essentially they start with sulfur. They react it with oxygen to form SO2. That's one step. Then they take the SO2 plus oxygen, and you can balance it yourself to go to SO3. Then you've got the reaction there occurring there. Water plus SO3 forms sulfuric acid. Okay. And remember, Hess's law fits. These all will add up essentially, but essentially you go to sulfuric acid now. You take the calcium phosphate, PO4, plus the sulfuric acid, H2SO4, you end up getting calcium sulfate plus phosphoric acid. Okay, and you can balance the equations. And then ammonia is then reacted with the ammonia here, 2 ammonias plus hydrogen phosphate. Okay, will essentially lead to 2 ammonias plus hydrogen phosphate will lead to your product at the end. And this is diammonium phosphate, which is very important. This is a very important fertilizer used on fields. Okay, and this comes out of what's called phosphate rock. And all these steps, this is called a mechanism. How did that reaction take place to go all the way to that other form? It went through a series of steps to get there. It's not possible to go directly to it just by reacting with the ingredients. You can't just react it with ammonia to get your product. You've got to go through a certain series of steps to enable that to occur. That's called a reaction mechanism. The sequence of elementary steps that lead to the product is called the reaction mechanism. Okay, let's give an example here with nitrogen oxide plus oxygen. You have N2O2 is detected during the reaction, so it must not go in just one step. So first you start off with an elementary step, which forms the N2O2 like that. And then you'll have a secondary step, another step, which reacts that with oxygen to get your product. So essentially you have the two NOs reacting together to get the N2O2 plus the other one together. Those are two steps. And the thing that's interesting about this is sometimes you can have a slow step and a fast step. Okay, and for example, if you are cooking hot dogs and putting them in buns, you already have the buns pre-made, and the fast you can do takes how much time it takes to cook the hot dogs. So basically one of the steps, the bread is already provided for you, or if you were to break the bread and then make the buns, that would be a lot slower. And then the fast step relation to that would be the cooking of the hot dog. But that's an example I like to use with my students to help understand the slow and the fast step associated with this. The overall reaction is this, because this essentially will cancel out on both sides as you add them together, and then you get your product. Okay, so let's look specifically at the reaction. The mechanism there, you have two NOs go to N2O2. The N2O2 reacts with oxygen to form nitrogen dioxide. Intermediates that occur in a reaction are not in the overall balanced one. An intermediate is always formed in the early elementary steps and consumed in a later step. Okay, so essentially it could be like it could be like this, where you start with NO here, two of them. It goes up to the intermediate step first. Okay, so you got your first N2O2 product there. The reaction then continues and goes like that. So now you've got your 2NO2 down here in the conditions. So you'll have two activation steps associated with that. So that's another way to look at the mechanism, is that kind of formula. Okay, so you have those two. There's the molecularity of reaction is the number of molecules reacting in an elementary step. Unimolecular is just one molecule. A bimolecular one is with two molecules associated with that. And then you can have 3 and 4. The rate laws and elementary steps. Unimolecular reaction goes from A to products. The rate will be equal to K there. Bimolecular, of that, you'll have K goes A and B, the concentration of both. This kind of reaction is dependent on both concentrations, concentration of each one. A bimolecular reaction goes to products there. If you have two A's, that would be A squared. And writing plausible reaction mechanisms, the sum of the elementary steps must give the overall one for it. The rate determining step should predict the same rate law that's determined experimentally. And the rate determining step is the slowest step in the sequence of steps leading to the product formation. Sequence of steps in studying the reaction things. You first start by measuring the rate of a reaction. You then formulate the rate law and then come up with a possible thing that occurs to do that. Okay, so basically with a very simple reaction like this, hydrogen plus chlorine, essentially they will collide. So you get the hydrogen collide with the chlorine like this. This is simple. You have just the right orientation for them to come together. Then you have the two HCl over the other side. So essentially the curve will look like this, with this being the intermediate stage. So that would be a very simple one. And that would be dependent on, this rate law would be dependent on the constant times the concentration of hydrogen times the concentration of chlorine there. Okay, and this theoretically would be 1 and 1, but you've got to determine it experimentally to be sure. And then you figure out what a reasonable reaction mechanism is it. They determined that it is 1 and 1, and that kind of indicates that the simplest one that we have there is the reaction that occurs for this typical reaction. Let's look at this reaction between both of these. The experimental rate law between NO2 and CO to produce is NO-CO rate is this. Now, the key thing to understand is when you have these different reactions, essentially the way you would do the rate is K equals NO2 squared, sorry, the rate, let me delete that. And this is important, very important to understand the nature of what these things look like. Essentially, the rate is going to be equal to the first one, K, times the concentration of NO2 here to the second power, and the concentration of CO will be to the 0 power. What is that part equal to? When anything to the 0 power is there, so essentially this is going to be equal to 1. So essentially this gets removed from that. That's the nature of that reaction. It's theoretically to occur during 2 separate steps. So let's look at the equation for the overall one. Okay. This is the overall reaction between both of them. What is the intermediate form? NO3 is the intermediate form. So when you have here the NO2, when you have the NO2 over here plus the CO, the intermediate form will be NO3 up here. That's the intermediate form first. And then that'll react with CO in the system. So essentially you're going to have first two NOs here, 2 NOs reacting there to go to NO3. Then you add the CO in this as well for the next part of the reaction. So essentially the intermediate would be NO3. What do you say about the relative rates between step 1 and step 2? Because the rate of KNO2 is the rate law for step 1, so step 1 must be slower than step 2. Step 2 is going to be instantaneous, and essentially this step 2 goes very, very fast. This is the fast step, this is the slow step. But basically, once you have that NO3 reacting with CO, essentially with the NO3 plus NO3, it reacts really quickly to get your other material. So let's look at this example here, the reaction progress going from one thing to the other. Okay, you have this, you add energy to it. This causes one of these to break. It breaks down like that. And then the other one like this. Essentially, you have this intermediate form, then goes to there. So how do we look at that? So basically, there are 2 possible mechanisms for this to occur. These break and then new ones form there. And basically, the first thing is the dis bond would break then, and then you end up getting this one break, and then you get that related to that. So the reaction progress may be a little bit more complicated than we think. A catalyst is a substance that increases the rate of a chemical reaction without itself being things. And basically what it does is it provides another mechanism with a lower activation energy. Okay, so if you got one reaction that occurs like this, and you got this activation energy that's relatively high going down to the products, and then you add the catalyst, essentially you will get now a new reaction curve that will look like this with it relatively low, and essentially this will change here. This activation energy will change to be a smaller one over here. So this is smaller, and the mechanism for that is going to be different because it provides the intermediate there in that system. Okay, so if you look at this reaction here, the Arrhenius equation, the activation energy coming down, the K will go up. This is uncatalyzed. This again is what I showed you here. You add the catalyst to it. I've got to fix this slide. As the activation energy goes down, sorry, this slide is, I've got to fix this slide here. So let me fix the slide. That's what the problem sometimes with these slides are. Okay, I'll go back to this slide now and share it with you. Okay, a catalyst is something without it being consumed. You have that relationship between as the activation energy goes down, the K goes up. You have uncatalyzed and catalyzed there. So essentially the catalyzed one has that activation energy that's less than the other one. I got to fix the slide again. Okay, you have this together there. The activation energy goes down, the K will go up. This is the catalyzed and the uncatalyzed reaction. The uncatalyzed is over here with the large one, and the catalyzed like that. So essentially, this is all sort of flipped around there. Well, apologies for the timing. Okay, the rate catalyzed is greater than the rate uncatalyzed. Heterogeneous catalysis, the reactants and the catalysts are in different phases. And an example of that could be like hydrogen reacting with chlorine. And then you have a platinum surface. This would be platinum. And essentially the hydrogen will kind of attach to the platinum. And then the chlorine could come in and orient easier with this and then form the 2HCl coming off. And that is a heterogeneous catalyst. These are both gases. This is a solid. So in the case of platinum, the reaction would take place faster. Haber synthesis of ammonia, and then Ostwald process for production of nitric acid. If you want, you can look these up. Homogeneous catalyst, the reactants and catalysts are dispersed in a single phase, and basically it uses a liquid, and basically then you would have little particles in a solution. You have like the lab we did before with the potassium chlorate in there with the manganese dioxide. That enabled the reaction to occur better. And in this case, you have both of the same phase, and these were both in the solids. You heated it up, it liquefied, and then you ended up with these interacting together, and then you got the oxygen coming off. That was what you did with the homogeneous catalysis with the previous experiment with those things melting. Acid catalysis and base catalysis are two examples. Now, one of the examples here is what's called the Haber process, and basically it provides it so it'll occur at a relatively low temperature. You've got this with the substrate. This is a solid substrate, and then the gases come in next to it. They orient on the catalyst itself. Then you get the ammonia coming off, and that essentially makes the process a lot easier for that reaction to take place. The Ostwald process is another one with a platinum catalyst, and then you've got the reactions between both of them together, and you can see the different reactions that would take place to get these. And then catalytic converters have catalysts inside it, and then essentially you get the hydrocarbons finishing the burning process, and nitrogen's converted to the nitrogen oxides are converted to nitrogen and oxygen gas. Enzyme catalysis is another example. Again, you've got a substrate and then the products coming off, but the enzyme acts as the catalyst in those cases. So then we got the binding of glucose to hexanase, and again, that is a catalyst process that essentially fits in really well, and then you can get the glucose to be decomposed. Enzyme kinetics, you have these relationships between them, and the rates are related to each of those. All active sites are occupied at and beyond this substrate concentration. Okay, so we are done that for today. If you have any questions, please email me, and I will be glad to answer any of your questions that you may have.